what sources they used.
Right. Very cool. So maybe we'll start with introductions then, and kind of again, like this is going to be really the hardest part of this meeting is how do we get everybody exactly once. We'll see how this can go. So maybe I'll just start. Right. So I'm Alexey Krabrov. I'm basically co-founder of this Quantum Conversations with Sebastian Hassinger, who is director of academic partnerships at IBM. Right. So we kind of ideated how to do a community around this. We planned physical community, but obviously pandemic interfered, and so we ran it online. So this is actually the 6th Quantum Conversations we did this year. So we tried to do it the last Wednesday of the month. The previous last Wednesday hit Thanksgiving holidays in the US, so we kind of just skipped it all together and sort of kind of breaking the cadence, right? So we'll just stick to the last Wednesday of the month if that works kind of for everybody, right? That's very easy to remember. 9 a.m. Pacific, we kind of capture a bit of Europe as well. So I'm a learner. I'm a software engineering guy. I'm kind of previous life I was a physicist, so tensors and matrices are not scary to me, but all the crazy jargon built on top of it for quantum, I didn't get to that in my kind of regular education. So I'm super interested in reconnecting with all of that, and kind of my whole family are physicists, and so kind of this is really cool for me. Kind of come back from software, pure software, traditional Silicon Valley kind of environment where it's like everybody kind of programs and it's all easy, kind of what to do. How do you do this here? Right? This is a question for me. There is so many diversion paths. You start, it's like a rabbit hole after rabbit hole. You start clicking on Wikipedia entries and they click on other Wikipedia entries, and after a while you're kind of you're somewhere else, right? So that's my problem. Like I really kind of, my question is, and I also want to know in a very tangible way what happens, and I don't see this currently in the educational materials. So like I want to understand exactly how do you input things into quantum computer, what runs and what comes back. And so I don't see that addressed in a lot of materials, right? Like they talk about qubits. Honestly, I don't care how qubits work. I'm a programmer. I don't care about how transistor works, right? I want to know how do I input things, how do I program the thing, how to get the output. This is what I care about. And this is not addressed by a lot of the stuff because it's done by physicists, right? So that's kind of my gripe and my question. So sorry, that was a very long introduction, but maybe like guys, you can kind of introduce yourselves and basically like ask like what's the main problem for you? Like what do you want to learn, right? Maybe that can be a pattern.
Alexey, okay.
Yep. Okay, so let's see who's gonna be next. Maybe we'll go with June. June Power.
Can you hear me?
Yep.
Okay, hi. Yeah, so actually I kind of agree with you. My background's computer science, and I did physics and math and done a lot of software. And I'm just really interested in quantum computing, but I'm like you. I really want to know like how you put things in, how things come out, and and also if you know some really good places to kind of get up and running with it. I did some quantum mechanics, in my undergraduate days, but I just think this area is so interesting and exciting, and I'm just interested in hearing people's experiences and what they think. Anyway, that's me.
Thank you, June. Next is Ameya Nambisan. Ameya, can you hear us? Going once. Going twice. Okay, we'll skip to Augusta Kleibovitz. Kielbovitz, sorry.
Okay, no problem. I don't know even how to pronounce it. So, yeah, I'm come from physics. I did my master here in Buenos Aires, and now I'm doing software engineering and finance. I really enjoyed all the topics that I learned about quantum things in college, but it gets there. It's like you have two options: to be a theoretical one doing some calculus and multiplying a few matrices, or you can have a lot of headache aligning optic things. So I went to software, and now that I have the chance to do a little bit in JP Morgan before, and they are starting a few things there. But I left the company, so I'm going on my way. And I tried to do like little things on that, but yeah, my main question is how to use it, how to make it available, and how to like have these abstractions, because like computing is so advanced. It's not again going through the same thing as C. You're programming in C, but with quantum computing, there's like you can have higher abstractions, and I am really interested in this ZX calculus. So I'm very hopeful to have something to learn from that. Yeah, that's mainly my.
Thank you, Augusta. Thank you. Next is Barzhan.
Hi everyone. My name is Baujan. I'm from Kazakhstan. So my background is electromechanical engineer, and now I'm working like software engineer in finance. And before I have a little experience in physics, like a little bit scientist, and I have a small experience with cryogenic facility when we tested a small chip like quantum chip, when we estimated some values. So now I'm very interesting to start learn quantum computing inside. So it's my show.
Thank you, Barzhan. Welcome. It's great to have you here.
Thank you.
Next is Brandon Kretschmer. Okay, my Brandon doesn't have a mic, so he texted us. Next is Dmitry Izumskiy.
Hello. So I would say I really kind of curious mostly about application of quantum computing, and I would say mostly it was like on my long-term goal to learn, and I'm kind of became more curious because let's say a couple months ago, one my software engineer actually started positioning IBM as quantum computer software engineer. And looks like stuff is changing very fast. So this is kind of my intention to spend more time to actually dedicate and figure out what it means from practical perspective.
Thank you. Welcome, Dmitry. Next is Dylan Mahoney.
Hi, I'm a freshman undergraduate at Stanford. I think I'm probably going to major in physics, and quantum computing and like quantum information science seems like a pretty interesting field thereof. So I guess I just kind of want to learn more about it.
Great, thank you. Welcome. Next is Jay McGill.
Yeah, hey everybody. I love this meetup. Based out of Wisconsin, and I'm in between undergraduate study and graduate study, but it's been a great year to soak up a lot of quantum computing content. So primarily I'd say this year, in my free time, I soak up a lot of different events and the different conferences and the different things that companies put on, tutorials and workshops and stuff. So it's a long journey, but my problem is I'm kind of interested in all of it because I started out as like a chemistry person who learned physics to understand the chemistry. And then once I got more into theoretical physics, I started looking at some, information theory, computer science type stuff. And along the way, I've done a little bit of coding, not a software engineer, but, it's just a blend of a lot of interesting areas. So still learning, still figuring things out, but it's just a really cool area.
Awesome. Thank you, Jimmy. It's like everybody, right? Like we all learn. So it's great. Next is Jean-Paul Sadia.
Hello, can you hear me?
Yep.
Okay. I'm an undergraduate freshman. I'm studying mathematics. I'm interested in kind of all the technologies that quantum can yield. But I'm also interested in the impact that the technologies will have. So, yeah, about it. Undergrad in math.
Awesome. Thank you. Thank you, Jean-Paul. Welcome. Jonathan Candelaria.
Yes, hi, Alexei. So I work at Stanford, but I'm really here to find out what everybody else's experiences have been, learning from mostly online resources, I think, primarily, and a lot of different, tutorials and webinars, but also the certificate classes that, MIT and Chicago and Berkeley and so forth have been putting on, as well as all the resources that IBM and others have provided for learning programming. But I'd like to hear just, for people from people who have taken those courses, do they feel like they're at a point where they're able to start actually doing something? Do they know enough to really do something, or are they still lacking something? And if so, what is that? And then we can talk maybe more about that. But I'm also here representing the QEDC, which is a national consortia of industry and academia and government agencies. And so I'm working in the Workforce Development Committee, and that committee is specifically aimed at wanting to learn these kinds of things. What education gaps are there? We know what the jobs are that are needed in industry. Mert knows a lot about that because he helped me put together a survey that we recently completed of industry, and so we know all about their needs right now and what they think the impact will be in the near to medium term. But are we ready? Do we have the workforce ready? And if not, then what do we need to do to help get them ready?
Hi, John. Thanks for joining.
Fantastic. Yeah, it's great to have you with us again. Thanks, Jonathan. Next is Kunal Marwaha.
Hi there. My name is Kunal. I studied physics and computer science in school. I was a software engineer for 3 or 4 years and decided I wanted to do something more mathematical. I have been doing some independent work in quantum computing, mostly in the algorithm side. Questions that I'm most interested in are, what can you do with a quantum computer that we don't know about yet? What problems are not solvable with a regular computer that you could do with quantum computer? And what are the relative merits of like current exciting quantum algorithms for near-term and for long-term computers? So I'm pretty interested on like the math side, but I also have a lot of interest in open source. And I'm sort of curious, like, if anyone's used Quantum Country by Michael Nielsen and other like online resources similar to the last speaker.
Thank you, Kunal. Yeah, this is like our all great questions. I'm sure we're all asking them as well, right? So that's great. Thanks for kind of summarizing this so concisely. Next is leelavathi yartha. Leelavathi.
Hi, I'm Leela. I'm a parent of a 14-year-old boy who is a freshman at DVHS San Ramon, California. He's very much interested in math and computer science. He has exceptional knowledge in physics as well as astronomy. It was just since his childhood, we encouraged him to read those books to improve his reading skills, but he went beyond that and he's very good with that. He has so many questions on those, and we introduced him quantum computing a little bit, what it is and what is the difference between computer science and quantum computing as well. So I'm just wondering what kind of resources he would have to improve his knowledge without depending on any school or anything, as well as do you have any resources for high schoolers to get them introduced to quantum computing and understand what is the benefit of it and how they can improve their skills and get into that field?
This is awesome. Thanks, Lulu, for joining. I mean, I wish every parent, would be as good as you. I have a 12-year-old son. He's not yet there, I would say, but this is awesome. Absolutely. I mean, feel free to invite your son to join us as well, right? Because I guess this field is new. I have a feeling that maybe somebody fresh who did not really get kind of conditioned in the old school maybe succeed even better, right? Because you don't need to rewire all your neurons, right? You don't have to assume things are as they are. I think a lot of problems come from that, but that's awesome. Welcome. So next is Mert, and Mert is also the co-organizer of Stanford Quantum, and he will be the first kind of lightning talk presenter today.
Yeah, hi everyone. I am a master's student at Stanford. I will graduate in a few days. I also did my undergrad at Stanford in physics and symbolic systems. Symbolic systems is Stanford specific major where we take classes from computer science, philosophy, linguistics, and psychology. So it's an interdisciplinary major. And I'm one of the founding members of Stanford Quantum Computing Association. And yeah, I just want to talk about a few resources that I used when I was learning about quantum computing. So I am a student of quantum computing.
Thank you, Merit. I'm looking forward to that, and really appreciate kind of jumping in on a rather short notice before the holidays. But this is awesome, and we have a couple folks left. Nathan Schor.
Hello, you can hear me, I take it?
Yes, Nathan.
I'm a bit of an odd bird from you guys. I'm in my 70s. I have no math and science background no math or physics formal background. I did IT marketing and sales, but I've had a lifetime fascination with math. I've always liked it since I was a kid. And now that I'm in the winter of my life, I decided, what am I going to do? Quantum computing is the intersection of physics, math, computer science. So it seduced me 2 years ago, and I started learning on my own. And I've gone through the learning curve quite intensely. It's all I do all day. In fact, I have a resource that I'll post on the chat called quantumcurious.org, where I've collected mine and many other people's experiences in climbing the curve. And there's lots of resources there curated for beginners. So I'll post that as time goes on today.
Thank you very much, Nathan. And I got your email, a lot of
good.
In the community, right? So really appreciate you joining. And I think this is really awesome, right? Like we have 14 years old, we have 70 years old. I mean, this is for everybody, right? This is it really connects a lot of folks. So really appreciate everybody joining. Really looking forward for, connecting with you in the community and looking at your resources. And our last intro is from Rishi, and Rishi is also a lightning talk speaker. Take it away, Rishi.
Hi everyone, my name is Rishi, and I'm a recent master's graduate from Chalmers University in Sweden. So my bachelor's was in electrical engineering from India, and all the physics background that I had was like basic physics 101 courses that you have, and some quantum mechanics, very introductory quantum mechanics courses. I recently graduated from the Erasmus Masters in Nanoscience program. And even there in the first year, we didn't have a lot of quantum mechanics. But then I came to Chalmers to specialize on quantum computing. And then it was like, poof, you were expected to know so much. So I had to rely a lot on online resources. And so I'd be talking about a few of those that worked for me, hopefully, and that'll be helpful for others too. Looking forward to this. Thank you.
Fantastic. Thank you, Rishi. Yeah, so basically, we've been very fortunate, for the session to seed it with 2 lightning talks by Merit and by Rishi. And then we can just all jump in. So maybe let's just do that, right? Merit, maybe we'll start with you and we can have discussion, and then we'll proceed with Rishi's lightning talk, and then we can all using all what we learn, maybe we can all jump in after that. So take it away, Merit.
Yeah, thanks. So I want to start with a quick poll. If everyone can either shout or write to the chat their main resource for learning quantum computing, what they use. It can be a book, it can be a website, it can be anything, basically. So mine was, I would say, Nielsen and Chuang's book on quantum computation and quantum information. Yeah, exactly. That's what I'm getting mostly. Exactly. Yeah. Great. We have MIT XPros 4 course series. Qiskit videos on YouTube. Okay, that's the programmer's approach that Alexei was talking about.
That's a good one too. It's a Quantum Mechanics Theoretical Minimum by Susskind and Friedman. It's a popular book, but it's a good introduction.
Interesting. Okay, so I'm just gonna like give an overview of some of the. I just like accumulated some resources, and I can email this to anyone who wants the formal document. Let me put my email on the chat. Okay, so but I'm just gonna talk about them. So I don't have a document that I can share right now. But so okay, so the textbooks, right? Let's start with the books. So I have a few books here that I wanted to share. So this is Nielsen and Chuang's book. It's pretty old, but it's always the first and the main resource for people who are starting in quantum computing. And I think it's more, I can say it's more computer science oriented, but it also has some physics. And for people who want to learn physics, okay, let's do this. So this is, as Alex showed, Mike and Ike, Nielsen and Chuang, the main textbook. And then for the physics people, this is the quantum mechanics book we used at Stanford, Griffiths. It's an introduction to quantum mechanics, and it's pretty solid. It's not directly applicable to quantum computing, but I use a lot of quantum mechanics. I used a lot of it when I was learning about quantum computing, and it's my favorite textbook of all time. So I would highly recommend it to people who are interested in the physics of things. And on the other side, we have Jack Hidery's book, Quantum Computing: An Applied Approach, and this is for people who just want to learn about the programming and be more on the practical side rather than theory. And it has a lot of examples from Google Circ, as Jack is associated with Google. And also on the fun side, we have Scott Aronson's Quantum Computing Democritus. And this one I just started. I haven't finished it. So if anyone has read it, please say something about it. But it's more, I think, math oriented. Scott is a computer scientist, I think. So
yeah, I read it last year. It's really good in introducing all the concepts. It's mainly focused on complexity of algorithms and what are the different classes of this algorithm, this complexity classes. It's really interesting. I had it a little harder to read because I don't have any computer science background, so it was like a step by step. But he has like a very good blog and his own like complexity zoo, so you can go there and look into the things that he's talking about. Yeah, that's really cool, and some conclusions that are really good. Yeah, and interesting on topics like the multiverse and all facts built from the quantum computing and complexity thing. It's really fun to also to hear their his interviews in podcasts and on shows. It's really nice.
Cool. Yeah, I should read it. All right, thanks. And then this is also one of my favorite books of all time. I wouldn't call this a textbook, but this is more for people who are interested in the philosophy of things. So this is a history of physics book and also a philosophy of physics book. So it talks about the interpretations of quantum mechanics, what it all means, but it's also like very physics oriented and ends with quantum information sciences and quantum computing. This is actually the book that got me interested in quantum computing. So I was taking a philosophy of physics course my freshman year at Stanford, and around the last chapter of this book talks about how David Deutsch argues that quantum computers are proofs for the multiverse interpretation of quantum mechanics, because to have that much computational power, the computer must be harnessing the power of multiple universes. So that's his argument. Also, I just started a book by David Deutsch. It's called The Fabric of Reality, and it's going pretty well. But that's the philosophy of things. So these are all books. I mean, you can everything is online now, so you can buy them or have other options of obtaining them online. but yeah, they're great. I mean, textbooks I think are great. I'm not a new school kind of person where I believe in the anti-textbook philosophy. I think textbooks are great. So other than that, so I'm gonna go with the I'm gonna get more decentralized. But as we go on, I want to talk about university lectures. So so I was a TA for a class at Stanford. I can ask the professor to maybe share those if you email me. I'm not sure how that would work, but I don't think that class is public. Some of Stanford classes are public, but we use a lot of material that's public, so I can give those. So Carnegie Mellon University has lectures that I used while I was preparing PSETs. MIT obviously has by Scott Aronson. That's a bit dated as well. I don't know if University of Texas lectures of Scott are published. And then there's also, I think, lectures from Delft that I used. But again, like if you email me, I can give all of these to you as with the links and everything. So let's move towards the online web pages and stuff. So Nielsen has a blog, and I'll share that at the end of this talk, but in the chat. But it's a bit old, and he has a YouTube series, and I think he also started Quantum Country. Thanks, Rishi, for summarizing the books. So Nielsen's blog, I haven't watched those videos. I think I watched the only first one, the Introduction to Qubits video, but he is the writer of, he's one of the authors for the main textbook for quantum computing, I would say. So those lectures, if you're more video oriented, they would work really well to complement maybe some of the stuff on the book, in the book. And there's also Scott's blog, Scott Aronson's blog. If you just Google Scott Aronson blog, that's more for keeping up with the news, what's going on. It's also more on the theory side, but it's really fun to read. I think it's a really fun read. So you could also keep a track of that. You can log in once every week and see what's going on in the both in academia and the industry. There's also yeah, again, Quantum Country, and also it's great that Nathan Schor is here because I was gonna mention Quantum Curious. Nathan just started that with Terrell Friends. That you started with Terrell, right, Nathan? Or am I wrong?
Yes, you're right. I use Terrell's data as a front end.
Perfect. Yeah. So yeah, John also knows Terrell. And sorry, go ahead, Nathan.
Terrell has a site called Quantum Appaloosa. It's
Yes.
very intense. It lists hundreds of things. It's raw HTML format. A lot of work went into it. So what I do is I filter out and he's broken things down to 3 or 4 categories: Quantum Curious, Quantum Explorer, and so on, all the way up to Quantum Pro. So I've taken the first layer, Quantum Curious, and I curate those events as well as all sorts of other resources.
Yeah, so yeah, that was next on my list, Quantum Appaloosa. Again, I'll share these links. That's you could also check that out. Terrell is a professor in, I'm not gonna say, I don't want to say anything wrong, but physics or computer science.
Harrisburg.
Sorry?
Harrisburg.
No, oh yeah, but I was talking about not the university, the field.
Computer science.
Computer science. Okay.
Cybersecurity.
Great. Perfect. All right. So you can also check that out, and there are like many online resources. And then we also have some resources from the industry. So for example, I attended the IBM summer school, which was great. We had a lot of like practical stuff like labs, and then also lectures, 3 hours lectures every day for 2 weeks. And it ended with a career lecture. So how to get into the quantum computing industry. So that was also great. It was actually overpopulated. IBM initially created this for around like 300 students or so. And then I think 5,000 people tried to join. So they had to like change their whole infrastructure overnight, and still they couldn't have everyone attend at least the labs. But I was lucky enough to get into the labs. So that is actually great that we have so many quantum curious people, as Nathan's site is labeled. And then there's also IBM Challenge, so that you don't have to wait until every summer to learn about quantum computing. But IBM also has challenges, I think a few times every year, that you can also do these labs and submit your responses to get certificates. And lastly, there are tutorials on every language. Most big companies like Google, IBM, they have their own language like Circ, Qiskit, and they have their own tutorials. So comprehensive YouTube videos, and then stuff that you can just like Jupyter notebooks that you can just download and play with. And lastly, there's also the free trials of every major hardware provider. Like if you go and sign into any hardware provider like D-Wave, that's open to public, or IBM, you get at least around 1 minute free time that you can use. So I would highly recommend playing around with a computer. That's right now free and available. Oh, also, that wasn't the last. Sorry, I have a few more. I have a second page. Feel free to join in anytime, please. And Alexei, if I'm going over time, please say so.
No, we're really informal. So guys, like, please,
yeah.
Sure.
So there's also conferences. One that happened very recently was Q2B by QCware. So that's my ex-employer. I worked for them for around 5 months as a part-time researcher. It's more business oriented, but it's also, I think, great for people who are just entering the field, because it's not highly technical for business people. So I think it's a great entry point into the field. D-Wave also had one. So my research was on annealing. D-Wave provides annealing methods. So there are 2 methods in quantum computing. One is gate-based, one is annealing-based. And actually, you could put topological methods into another category. But anyway, so my research was on annealing, and so I attended the D-Wave conference. That was really helpful for me. There's also a Unitary Fund that also does talks like we do. Researchers come in and share their projects. That's on Discord. Unitary Fund is created by Zhiyong Zhang. And there's, of course, the Stanford events, the Stanford Quantum Computing Association events. And you don't have to be a Stanford student. So just before I graduated, I tried to open up our events as much as I could. Our last event was with Andre Koenig and Denise Ruffner. Denise just joined INQ from Cambridge Quantum Computing, and Andre runs One Quantum. We also created we organized a quantum chess tournament, and that was across universities, but it was mainly Stanford and Berkeley. It's disappointing for me to say that Berkeley won the tournament. We had Stanford versus Berkeley at the final game. And then we have many more events. You can join our newsletter. I can also put that link down here after my talk. And there are also articles, lastly. So if you're more into if you have one niche field that you want to really learn as much as you can about, like my field, my research was on reverse annealing, which is even more particular than the whole annealing field. And there's, for example, Zhiyong Zhang that I just mentioned, who created Unitary Fund, has a paper called A Practical Quantum Instruction Set Architecture about the language and compiling of quantum computing. There is also Google's TensorFlow quantum paper. That's also really cool. And then there are many more papers that are intro level that one can read about, and they're all online. Like you can do that right now. Go to archive and search for these names, and you will find the papers. So overall, how I did things and how I would do differently is that I think, and many people who go to like who go to these resources to learn, it's really like fun and games. Like you can have fun while learning, and obviously we are all interested in this field. That's why like you are attending this talk. But I think that people learn best when they have projects with concrete goals and deadlines. So I think that's what I realized when I did my research at QCware. Like I learned so much because I had to make those deadlines. Like I had the presentation to show every week, blah blah blah. So like those worked in favor for my learning. Whereas for that, I mean, personally for me, if I have like a class, like homework, a test, or a presentation to make, I'm more motivated to learn. So my advice would be to like try to get yourself involved with these projects. There are like many open source projects right now that you can just get into going into GitHub and like starting contributing on a project. One example I would give to that would be the quantum chess repo that we used. That's actually half finished, so it has superposition but it doesn't have entanglement. And the person who created it obviously did a great job, but it's not finished. And the last push was made in 2016 or something. So like if you're interested, you could just like start coding this up, and there are also many quantum simulators that are online. So you could easily assign yourself a project, and I think that would be the best way to learn about these things.
Now, I would like to say in this line of thoughts that Quantum Open Source Foundation, and I post a link, they have a mentorship program where people are mentoring mentees that are interested on specific projects. Usually people go through some kind of selection process to see their level of understanding quantum computing and what they're interested in. At the moment, I'm, for example, mentoring like 5 people that I selected that are relevant to what I can mentor with respect to their interests. So that's one place you can consider to get into the quantum computing realm.
Yeah, thanks for sharing that. See, that's great. So I didn't know about this one, but there are so many resources, and I think again, the best way to motivate for me to motivate myself was to have a concrete project, and that's with deadlines and deliverables. So that's all I had, and yeah. So I don't want to be the one that's doing the talking on me.
Thank you, Mert. That was a fantastic start and a great overview of of the books. I just went and bought a couple on Amazon as you was talking about them because I didn't know about them. So I'm this kind of a guy. I hoard books. So I'd rather have a book and like look at it than not have a book and wonder if I should have had it. So, but then that's just me. So thank you. So guys, I guess we can do it. Maybe if you have questions for Mert, right, we can do like a traditional Q&A if you guys have any questions, or we can hear Rishi, who is another lightning talk speaker, and maybe we can like do Q&As to both of them after that. What do you guys think? Anybody has pressing questions to Mert right now?
I have one quick question.
Let's go ahead.
It's John. So Mert, you said that you took the IBM summer school. How would you characterize that course compared to what you learned at Stanford in the courses there, or maybe the books that you've been reading? I mean, how was it similar or different? And what new things did you learn there that might be not available in any other form?
So, well, obviously the course was for like 2,000 people or something, so you didn't get a lot of you could maybe I didn't, but like it's not like a 30-person course where you can talk to the professor throughout the course, but you can like text your questions or something. I know I think it was still self-learning in some sense, so you're not like being fed the information, and you don't really have to like, if you're not self-motivated, you don't really have to like in courses like this, you don't really have to like push yourself to learn more, or like even like finish the course. I mean, I got a certificate at the end, but it wasn't like that hard to get that certificate. Whereas a university course, then you have really hard P sets. At least our Stanford physics classes were a bit on the difficult side, and you had to like meet with other students and work on problem sets together. It wasn't a one-person deal, whereas IBM did a great job on connecting people over Discord, and everyone could like talk to each other, post their questions there. But again, that small community feel is really hard to find when this field has so much demand. People want to learn about it. So I don't know how that would be accomplished in a online setting. But yeah, that's like, I think it was very concrete in the sense that we had like daily labs. So every day we had to finish one lab that was a Jupyter notebook. So it was very similar to like university P sets. But yeah, again, I think it's really hard to find that like that feeling of having other people teach you, because you don't only learn from a lecture at school, you also learn from friends. Especially in physics, you learn mainly from like students who are struggling with you at 2 a.m. to finish that quantum mechanics P set. So I would say that we still like need universities, and that feeling hopefully after this pandemic will also be in classrooms. It's really hard to like cooperate through a computer screen, but yeah, that feeling of being in a classroom and working together through a P set is, I think, an essential element of learning.
So if I may add to that, that's a good question, Jonathan. Is that so? I didn't attend the IBM's summer school, but then there was I don't know if anybody knows about Q World. So they are also another organization that holds workshops and courses. But the course that they have now is like Q Bronze. It's a bit too simple, maybe. It's mostly aimed at high school students. So maybe leelavathi, this is something that's interesting to you, your son. And it starts from very basics like coin toss, and then tries to get people more interested into teleportation and couple more things. And it uses Qiskit, so it starts off very slow. And so if you already know what quantum is, and if you had at least one course, maybe this could be a bit too simple for you. But yeah, so they also have this thing. And I mean, so one good thing that I liked about or the one silver lining that I see about COVID is that a lot of things moved online, right? So I mean, otherwise, maybe I wouldn't even have been able to attend this conversations, because it's and so it was a really good platform for me to network and get to know people beyond the circle that I usually am in, right? So in that aspect, it was very nice. But then again, like Mert was saying, as far as learning goes, it's still very questionable. I too prefer working with my friends on problem sets, and then like of course. But yeah, this you get to know a lot more people, and then you can build on that. You can maybe you like some of the discussions that some people were having on the project, and then you can take that outside, right? You can take it and work on some more projects. So again, it has like pros and cons. So this is another aspect to it that I felt was nice.
Thank you.
Thank you. Any other questions for Mert?
No, but Nathan here, can I get up?
Yes.
But we've been talking about books as a common theme, and I have an observation about that. Mert showed a few of them. Despite the fact that I'm probably least on the list here in terms of STEM credentials, I'm inadvertently developed over the last 2 years an expertise. I've spent about 2 years now, as I said, reading quantum computing and quantum mechanics books to support it. So it's about 70 of them. On the Quantum Curious site, I've listed them all with some commentary. So I've developed a bit of an expertise. And a summary of that is the book for the average beginner, not the high school person. That's a different category. Not people with a physics or math background. That's yet another category. There's plenty of books for them. But for the average person, the Quantum Curious or the Quantum Explorer or the Quantum Enthusiast, that book remains to be written. That's a project I'd be interested in looking into if someone else knew someone who was working on that. A book for the average Joe, so to speak. Maybe someone with a college degree, but not a STEM degree necessarily. Mike and Ike's a great book, but it's for graduate level. It's really well written, the English. I mean, if English is not your foreign language, you probably learn more about writing English in that book than you might about quantum computing. It's really well written, but it's too advanced. And so are many of the others. So that's an observation.
Thank you, Nathan. Yeah, I mean, I see kind of approaching this area, there is no shortage of angles from which it can be done, right? So I think currently there is a lot of things for physicists. I personally see huge gap for software engineers who have very kind of specific and pragmatic needs, right? So I am sure there can be a lot of other interests. Hopefully, as a result of this, maybe some of the folks here will do that. So maybe we can now let Rishi the floor, and after that we can all just have a general discussion. What do you guys think?
Right. So just to comment on Nathan's earlier statement, maybe Nathan, have you heard of this community called Quantum London? So they are also more business-oriented people, and I think they may know a bit more about. So if you would like to speak to them, then maybe I can send you their contact. And it's available online. So
that's Quantum London, as the city London in UK.
Yeah. It's Paolo and M. I don't know M's full name now, but I can write it in the chat towards the end while we are having discussions. And also there's Quantum Tech Daily, again from London. So yeah, it is few, but people are trickling in from non-technical areas, which is really nice, because to have a proper ecosystem, you need people from all aspects, right? So right, yeah. So now maybe I'll share some of the experiences that I've had learning quantum computing. And I don't know how popular a take this is, but this is, and it's not mine, right? It's Scott Aronson's, and Scott says that quantum computing and quantum mechanics becomes a lot more simpler if you take the physics out of it, right? So, and I agree. So for me, my background was electrical engineering, and it was not even electronics where you have some CMOS stuff going on. It's like big DC machines and outdated stuff. And yeah, let's not go there. But I would say that one of the biggest prerequisites for learning quantum computing would be linear algebra, right? It's, I mean, what I felt is that quantum computing is linear algebra being very fancy. And so for that, because, I mean, yeah, let me motivate that maybe then. Because your quantum states and everything are like vectors in some vector space, in a Hilbert space, and all the gates that you apply or transformations to those vectors. And your vector goes from one point to another, and things move around. And so you can get a very better I mean, you can get much better intuition as to what's going on if you know linear algebra. And so in linear algebra, you talk about eigenvalues and eigenvectors and about basis transformations. And these things, or at least getting to be familiarized to these things, help immensely in understanding what quantum computing or what quantum mechanics is trying to say, right? Because yeah, so for that, I would highly recommend Gilbert Strang's online lectures from MIT OpenCourseWare. It's super simple. It starts off with vector matrix multiplications, and it just blows your mind, right? I mean, it's just it gives you different ways to think about vector matrix multiplications, matrix multiplications, and so on. And even like entanglement, right? So when you say quantum entanglement, it's like, ooh, spooky. I mean, but fundamentally, mathematically, it's singular value decomposition, and that's covered really well in the lectures, but towards the end, maybe like 26 or something. So I would highly recommend, and you don't even need to know physics or anything, right? It's
Whose lectures are those again? You said it quickly. Please say it slowly.
right. Yeah, sorry. Oh yeah. So maybe before this, so I started typing out all this into a list, but then I procrastinated a bit, so it's not finished. But I will type it out and I'll send it to Alexei, or you can I'll put my email also in the chat, and then I can send it to you.
Yeah, I'll get the list when Rishi sends it, and I'll post it on the website quantum.sv, our main website.
Right. And another thing is, so I don't know if everybody knows this, but you can save the chat to your own computer. You just go to the chat, and then there are 3 dots, and you click it, and you can save it. So that's something that maybe you could do.
Oh wait, I didn't know that.
Yeah, I didn't know it too. It
for
was
like
like each time I was copying and pasting it somewhere in the tab in in Firefox somewhere, but you could just save it, and it just saves a lot of time.
How do you do it again?
So you go to your chat, and then there's 3 dots in the right corner, like more. Maybe I'll just...
Okay. Anyway, I can figure it out. You can go on with your talk.
No,
Sorry.
yeah, it's just 3 dots, and it says more, and just save chat. Yeah. Right. Yeah, so singular value decomposition, right? And that gives you a completely new perspective on what entanglement is. And once you know sort of what entanglement is, then you can, then it's so much easier to sort of say what quantum advantage is, and or when your quantum computer sort of outperforms a classical computer and so on. So you start from some very basic stuff, and then you can get so much more insight than you started off with, right? So that's something I love. So linear algebra, and you need linear algebra everywhere, right? So machine learning, whatever. So it's one skill that is definitely never going to not do you any good. And so once you have that down, or even before that, so that was probably one of the biggest. It's like I forget the name, but the 80-20 principle. You 20% of the effort sort of counts for 80% of the results. This has anybody heard of this? It's some French mathematician or philosopher or someone who came up with this, and it's so yeah. So that was a large part of the 20% of my efforts was learning linear algebra.
That would be the Pareto principle.
Yes,
Pareto.
that's it. I didn't want to. Yeah, I don't want to not know the name. I mean, mispronounce the name, but yes. Right. And so the next thing was getting to know what the physics was, right? Because a lot of these, you start looking into quantum, you suddenly thrown at what Hamiltonians are and what excited states are and energy levels and so on. And so at Chalmers, this is one of the first courses that we had, and in the first lectures, the professor's like, okay, so today we'll quantize an electrical circuit and find what the Hamiltonian is. And I'm like, what's Hamiltonian? So it's, but then, and these are things that maybe physics undergrads deal with in their second year or something. So it's something very basic that maybe not many people talk about. And if I'm talking too fast, please tell me that, because I tend to do that. Sorry. Right. And something that really worked for me was Theoretical Minima by Professor Susskind and his classical mechanics course. Right. It was so good, and it was very consuming. Right. It's not something that you can just, or at least for me, it was not something that I could just sit and watch on a weekend to unwind or something. It was I had to sit down, and each lecture was maybe 1 hour 40 minutes or something, and it took me at least 4 hours to get through. Right. So I sit down and I write my notes, and it's you have to keep rewatching it. And this is after I watched it like at 1.5 speed. So it's but it's awesome. It's super good, and you get sort of an understanding of where the Hamiltonian comes from, right? It's and it's no longer some esoteric, like super fancy thing that people just say, oh yeah, apply the Hamiltonian. But yeah, so once you sort of know what a Hamiltonian is, and you sort of know what is the linear algebra or what is the math that is sort of going behind all this, then I would say you're in a good position, and you can at least start to be part of the conversations that happen around, right? And of course, it helps to have quantum mechanics courses, because then, and these things, right? This superposition and entanglement, and these things are not something that you finally understand. It's just something that you get used to, is what I feel. So you get used to it.
I totally agree with that.
Right?
I think it was Feynman who said, Richard Feynman said that if you think you understand quantum mechanics, you don't know enough of it or something.
Exactly, right? So it's I agree, and for me, it's always been, you look at the same concept from different perspectives, and things sort of start lightening up, and you sort of get more and more used to it, and yeah, you you carry on, I guess. Right. So for basic quantum mechanics, again, there's MIT OpenCourseWare. There's quantum mechanics 1, 2, and 3. I followed quantum mechanics 1, and it is already like, I mean, I had usual college work and this, so I was already way over my head, but it was super good, and I recommend it. But again, there are these resources are the ones that I followed, but there are a lot of others that are equally or more good maybe, and it works for you, right? And yeah, one thing that I was really happy about was I was worried that Mert and I may end up talking about the same thing, and nothing new. So I'm really happy that Mert's a textbook guy and I'm more of a video lectures guy. So I prefer video lectures, because that allows me to just sit with it, and then there's some interaction going on, and I have very short attention span, so it's textbooks. But again, that's personal preference, right? So now you have, or hopefully the people get to have a more wide variety of things to pick up from. Right. And I was writing down a few notes while people were talking about things that they may be interested in. And right before that, so yeah, with these 3 things, I think you're in a good place to so basic, you know, linear algebra, and with that you sort of know almost a lot of quantum computing. This is maybe a gross simplification. There are like very different niches and all those things, but at least you can be a part of these conversations, right? And then you follow Professor Suskind's course. So there is the theoretical minima, and it has everything. It is classical mechanics, it is statistical mechanics, it's quantum computing. It is quantum mechanics, it is entanglement. But for me, I think it would take my lifetime to go through all that, because it took me so long to just get through the classical mechanics one. But I would love to. It's on my bucket list. Right. And yeah, another great thing another great resource that I've loved is meetups like these, right? It's when you get to know people and you get to know sort of things that work for other people, and and it's been great. It's so I really enjoy that. And so like I said, one of the probably the only silver lining of COVID is that a lot of these conferences and talks are online, and you can share your space, you can share a room, albeit a virtual one, with people that you may never do it, right? I mean, in just last quantum conversations, in Alexei's quantum conversations, Eddie Fari was in the same room, and I was like freaking out. Oh no, Eddie Fari's here, because so I'm working with QAOA. I mean, I'm working on QAOA. My entire thesis is on QAOA, and people who know Eddie Fari is the one who made QAOA, right? So it was like, whoa. Yeah, but so that's super cool, and I love that. And so there are a lot of such communities that I would highly recommend people be a part of, because again, you get to see different perspectives, and then you get to talk to a wide variety of people, and that's super nice. For example, Nathan has a newsletter that I follow, and it's super nice. Go Nathan. And so Mert was talking about Andre and Denise. They also have the One Quantum organization, and they have a weekly, or yeah, I think it's a weekly show on YouTube, or so called the Weekly Quantum World Detangled, and it's an amazing resource. You get to listen to people who are in the top of the game, right? So you get to listen to CEOs or and from different parts of the world, and they're doing a really good job. So check them out.
Quick correction. It's not me. It's Nathan. It's not me who has the newsletter. It's Doug Fink. It's called Quantum Computing Report. QuantumComputingReport.com. I put it earlier in the chat.
Right.
And it's really worth looking at. It comes out on Sundays, and in 10 minutes, you get to view what's going on in the industry. Right. So for beginners, it's really well done. QuantumComputingReport.com.
Right, it's the one by ORNL, right?
Pardon?
No.
It's the one by ORNL. No.
It's the one by Doug Fink. It comes out Sunday. It's been coming out for a couple of years. It's free and really well done. 10 minutes, really worth looking at. You get a good overview of the industry.
Right. Yeah, thank you for that. But I remember seeing, so had you written about the One Quantum organization's Women in Quantum? Because I remember seeing an email from you in my newsletter. That's why I said it, and it was super cool, but thanks. Right. And yeah, so there are people also who really like to know how do I get started, or how do I start using this thing, right? I mean, yeah, there's a qubit, there is like superconducting, there's photonics. So for that, again, IBM's been doing a great job putting real devices in the cloud for people to access. That's super cool. It's anybody can make their own account in the IBM Q experience, I believe, and you can start using it. And Qiskit also is very well documented, and they have a really strong community going on. So Qiskit also has a Slack channel. So if you would want to meet more Qiskit people, join that. It's a great place. And also, so TensorFlow Quantum, right? So TensorFlow Quantum is what's really cool is that they have a weekly sync thing that is open for all, and anybody can join it, right? And you can talk to people who made TensorFlow Quantum, and you can be, at least for me, I've tried to join the past two syncs, and I mean, mostly I am a mute spectator because that's not what I work on, but it's awesome that you can do it. And so just the last sync, what they were talking about was Iadanis, Professor Iadanis from QCware, Mert may know him, was talking about loading classical data into quantum computers. And that's something that people are interested in, right? So, and then there was a discussion, then Google's Ryan Babush was there, Alan Coe was there, and yeah, you were there. I mean, you could be there with that team and just listen to all the cool things that are happening. So a lot of things are happening. It's good to be part of these meetup groups and so on, and that can help, right? And so it's I do agree that there's a very distinct shortage of not involving non-technical people into the conversations, but I think that's also changing, because in Medium I see a lot of these posts like quantum computing for the curious, quantum computing for dummies, quantum computing for the confused, and so on. And that's all that's been very helpful for me. So maybe I'll put that in my list, and then I can share it with you guys. and it's nice to see that there is some change happening at least, right? Right. Let's see this. So I talked about TensorFlow Quantum. Right, and Mert already talked about the QSF, the Quantum Open Source Foundation, and the Unitary Fund. So they also have a Discord channel where you could join, and then you could be part of the conversations that they're having, and so on. And so this Quantum London also holds monthly meetings like this one, and they're also a major chunk of the conversation is from a business perspective, I believe. Like, when will this start being useful? How do people get started, and so on. So it's and I think they call it Quantum Stummish. I'm not even sure if I'm saying it right, but it means it's like a roundtable conference or something, and it's pretty cool. And yeah, Augusto, ZX Calculus. I'm also super excited about ZX Calculus, but I'm also yet to start learning it. So my work is on tensor networks, and if people are interested, maybe we can discuss that too. But I think I've been talking on for a long time, and I don't want to put anyone to sleep. And let's see this. Yeah, so leelavathi, Q World is probably a good place for you and your son. And also this qubit by qubit that you shared in the chat. I think that's also mostly, I've not been a part of their lectures, but I think they're mostly aimed at high school students also. So I think you need to know what trigonometry is, but yeah. And yeah, so Q World also has this Q Intern program. So they had one chapter of that, I think, like one edition. It's just like the quantum mentorship that someone mentioned. And right, and then there is, so there are many communities out there, and there are many people who write about these things. So, and LinkedIn is a very great place to network, I would say. I mean, I don't know what people's opinions are of LinkedIn, but I really liked it. I started networking only like 4 months ago, because the pandemic hit and a lot of my plans went south. But I've been having a really good experience with it so far. People have been very helpful, and you reach out to them, they're kind, and then you be kind, and then you help, and then yeah. So it's been really nice. So I would suggest following Agi from Agi was previously a perimeter faculty, and now they're in IBM, and also a blog called Musty Thoughts from Michael Ketley. So Michael is also maybe someone who can have a lot of insights, because he was a software engineer for a long time, and then he shifted into quantum computing. And so recently he said that he would have a blog on how you can get started into being a quantum software engineer. And he was asking for people for suggestions on what they would like to see him write about, right? So yeah, sorry about but that's all I had to say, I believe.
Thank you, Richard. That was awesome. That was a great review. Question, so that you mentioned this talk about loading classical data into quantum computers. Is it available online somewhere as a recording?
I need to check that, because I know that they recorded it, but I don't know if they have made it publicly available yet.
Yeah, maybe
it's from QCR.
This is by Jordanis, right? Is
right,
that what
yeah.
Yeah. So I think Jordanis published on the subject, but I would add it to my Google Doc if
no, yeah. So they have published this. It's published, but if you prefer a talk, and it was followable, I could understand it, although I have zero experience on that side of things.
Yeah,
that was pretty nice.
I'd appreciate it. If somebody has a link, that would be great to follow up.
Right. I will put that in my in the doc. Yes.
Thank you.
Yeah. So people who posted in the chat for the resources, I think this is what we'll do. Rishi and I will create a Google Doc together, and then email us. We can share that with you. But Alexi, I think, has all of your emails, so Alexi can just send that out to you guys after we finish. Is that good?
I mean, the way we can do it, we'll just post the link on Quantum SV website, and then that will be available to everybody. So
website again? Quantum what?
Quantum.sv. That's the main website for this quantum conversation. It's I'll just type it in here. It's quantum.sv for Silicon Valley.
Thank you.
So that's kind of, it's a Tumblr blog. We currently just post the announcements and links, but we can also create a kind of resource section there, long overdue, and add the documents as needed. So I just wanted to kind of shift gears a little bit, and so it's, there is like a push and pull models of education, right? And so the classical education is a push model where the professors are pushing knowledge on you, right? And the professors arrived at it through a variety of ways. It's almost like a religion, right? Like the Pope proclaims encyclicas, and then they percolate down to the bishops and to the priests, and then they gather the masses. And like some of the literate peasants of Italy don't even know it's in Latin. They used to kind of just repeat the words without knowing the meaning, right? So in a way, that's kind of traditional science works. So, and the kind of in Silicon Valley, we disrupted this by having a bunch of folks just jumping in with journalism degree or like whatever, like reading a bunch of O'Reilly books, learning, open source languages like Ruby and Python. And so it's kind of more of a pull, right? Because you kind of come from the bottom up. So my question, and just feel free everybody kind of to ask, what's your most urgent question? What I found when I partnered with IBM, right? Like I did this before, and I generally run committed software engineers who are in this kind of pull model, right? Normally they're motivated by actual needs, because there is a whole economy of startups and enterprises, and stuff needs to be done, right? Like you come in and it's very clear, here's the business going on. You need to process this data, find out why are the customers not buying stuff, why are they leaving, why is fraud happening, right? Why is churn happening? Or you just need to convert a bunch of a terabyte of JSON into SQL, right? Like it's very clear what needs to be done, right? And so now developers come into this field with the same kind of mentality. They want to get their hands dirty, and then they immediately ask questions like, and it's always kind of, it's never getting, it's always fresh. Like people come in and say, what is the API? Like, is there a compiler, right? And I am kind of dumbfounded a bit, because I kind of know there is not an API or a compiler in the traditional sense. And so, but this question never gets solved. So kind of what I want to understand, let's say you are a developer, and so you have these very basic questions, right? You have the notion of a computer as an input and output, and a processor and a compiler, and a traditional computer have registers, right? And so somebody mentioned, like, we're in the ENIAC stage. Remember ENIAC, the first computer, at least according to the Americans. And so I actually went to grad school at University of Pennsylvania, and ENIAC is actually there at the Moore School of Engineering at the ground floor. And when there was the 50th anniversary of computing, according to Association for Computing Machinery, we had a visit from Al Gore, who invented the internet, then Vice President of the US, jokingly claimed, actually he didn't, but there was a joke that because he promoted important internet laws. And so the ENIAC was updated and restored, and actually counted from 1 to 100 for 100 years of computing, 50 past and 50 future. And so the ENIAC is programmed by basically connecting, like this telephone exchange, you can connect cables into sockets, right? And now that it just reminded me of the quantum gates, right? So kind of like one way we program things, we manually assemble this architectures of programs, right? And so are we at the stage of ENIAC? I mean, even at this stage, we don't need to know how transistors work or lamps, right? So developers, so it's like kind of, my feeling is, again, prove me wrong, but developers don't need to know how qubits work. They need to know some basic characteristics. The qubits are noisy, and basically, like, this is as far as probably they need to know, how reliable are qubits and what are the operations composing them together. It's just, the question is, how far are we from the point where, and first of all, what happens at the quantum computer? How do we actually make these architectures? Are they programmatic, or is there any hardware which needs to be connected using this cable? So like we're at the stage where the whole thing is in software. There is no need to do cables anymore. Or are we at this stage we still don't need to do cables? So what happens in a very basic form? You extract a bunch of data from your corporate SQL database, right? And you need to solve like a pharma problem, a protein folding problem, right? So I wonder why is there is no resource which tells you in exact excruciating detail what happens. You extract the data using classical computing, using JSON processing, Python, Java. Like here's where it ends. Here, what happens when you put it into the quantum computer. Here's what actually, happens at the physics level. Here's the interface. Like, so I don't know if just me, but I really need to develop a feeling where classical input is done and where quantum takes over. What happens then? Is the architecture of a quantum computer hardware configurable? Do you need to reconfigure it for a task, or is it fully software defined? And what does it mean? And then how do you capture the output, and how does it end up in a traditional SQL database, and maybe then on my MacBook through a browser? So I wonder if anybody can talk to that, right? Because I generally don't see that covered end to end. Right? People either zoom in on one thing or the other, but I wonder if did anybody see that? Is it a valid question to ask? Right? Because developers are asking this. So how would, does anybody here have an answer to that, or a pointer to if any of these resources help you to put together end-to-end understanding? So
I think I might have an answer to that, because you're asking about, I want to know how the process works from
end to end. Exactly.
End to end. Okay. So I think a way to grasp that would be working again on a project. And so I want to briefly mention something else. I think right now in quantum computing we have two kinds of people. One is the expert. So that person, for example, could be an expert in superconductors, right? And he or she could be very good with connecting superconductors to some part of a circuit. And that person doesn't need to know about the Grover's search algorithm. That person can be very good at their job. And then we have, I call these people conduits, if that makes sense, but they are the facilitators of discussion, and they connect the experts together. So these people are the people the people who write the books, and then the people who host stuff like you, Alexei, Quantum Conversations. So these people are more worried about the process. They want to know, or they teach what's going on in a higher level. And for me, I think the part where I understand one process fully was again my project on annealing, and I can get into the details of that process if you want, Alexei. But again, as an overview, that's when I learned about the whole process. What happens when I put so I start a Jupyter notebook, I connect to the D-Wave computer, I have a classical thing that I want to solve, and what happens from end to end. That's how I learned through a process in quantum computing. And right now we have to rely, I think at every point we'll have to rely on classical methods, because we are classical beings. We are not quantum beings. So we have to somehow transform that knowledge into stuff that's useful to us as human beings. So we'll always have, in some sense, hybrid methods, although we kind of divide methods into hybrid and fully quantum. I think it's always going to be hybrid because we are classical. But again, yeah, that's how I highly recommend working on projects. It's also good for the world to build something, and I think that's the only proper way to learn.
Very cool.
Alexei.
Thank you, Mert. I wonder, I mean, could we do something like that, given that, IBM supports us in the sense as a community, they probably can get us some access to the Q network. Can your project for annealing be reproduced on the IBM Q network? I wonder if, if there is something that, I mean, you can lead or, somebody can do, right, to give us the feeling like that. Is that something, I mean, was it a part of this IBM summer school? I mean, because I agree, doing a project would help, but obviously if you are new at this, you kind of spend an inordinate amount of time just staring at stuff, not knowing what to do first. So it would be best to have somebody, tutor and walk folks through something like that. So I wonder if, that's, if like what you did, was it highly bespoke and you needed to kind of do a lot of hard work figuring it out, or is this something which can be now followed with IBM Q network?
I could talk about it, but it wouldn't be replicable in IBM's hardware because they are gate-based. It would have to use another hardware provider, which is D-Wave, and I think they are competing with IBM. So IBM wouldn't like that too much, I guess. But but I would love to talk about the process as a part of a network. Yeah.
Cool. No, that's great. That's awesome.
Alexei, I'd like to address, unless someone else has something.
No, please go ahead.
Another part of your question, but I'll wait a second. Maybe someone else wants to jump in first who hasn't talked.
No, please go ahead.
I would have a question. I don't know if someone I put it in the chat. Can you hear me?
Yeah, we can hear you.
Okay. I was wondering if there's a kind of order of learning things. So a lot of people are starting at different parts of their education. They have different backgrounds. So I was wondering if there's an order for every person to get where they wanted to go.
There's an easy answer for that. It really, the obvious answer in anything, nothing to do with quantum computing. You're trying to learn something new. Chess, for example, which I don't know, and let's say I wanted to. It depends on your background and experience. You sound from your voice probably in the spring of your life, right? You're probably just finishing college in your 20s. Gene,
I'm actually just starting.
Okay, so even that's my point. I'm in my 70s, so right there's a big difference. Alexei's a professional. Other people are just in various stages of school. Some people are marketing people. Some are programmers. So I think an ideal path is a function of from whence you came. There is no one best path. Simply why there's no one best book. There's just more and more paths. In my opinion.
No, yeah, I agree with Nathan, but also there are some things that are maybe more fundamental than others. So I mean, maybe I'm very biased to how I did things, but I would highly recommend linear algebra if that is not obvious from.
I
wouldn't say that's
not obvious. With that, I agree. Linear algebra is necessary.
And since you're starting college, right? It's linear algebra is a first year undergrad course. So
also, fortunately, it's linear. It's easy, relatively, to other math. So it's in that sense, we're blessed. It's understandable. It's digestible. That's my word for it.
Yeah.
I mean, linear algebra is great and beautiful, and I think it makes things much clearer. But I wouldn't say it's necessary. It's not like an obsolete starting point.
It's not necessary. What would you replace it with?
As you said, I totally agree with you, Nathan. Like everyone has their own starting point. Everyone has their own path. For example, one person who doesn't know anything about linear algebra could open up IBM Q or something and spend their 1 minute of time following tutorials and coding stuff up. and just thinking of just circuits. No one has to know about a Hermitian operator, right? You don't have to know that. You can just code things up.
But true, yeah, in that sense, it's true. You have an interface. You have that orchestra, you know, that beautiful musical architecture they use. That's true.
Yeah, yeah. So again, it depends on you, Sean.
Yeah. I just don't want to, like, I love math, and I think linear algebra is like, it's beautiful, but
no, yeah, but yeah,
but
if
some
you
people would maybe like start the field from another perspective, and they might be again like an expert in their area, and it might be the case that they don't use linear algebra at all.
right, yeah, no, I so if you have someone who's more experienced coding stuff and looking at code and seeing developing your intuition from there, that also probably helps. But
I personally started at vector analysis and doing much matrix analysis now. So I took linear algebra.
Right. Yeah.
Yeah. That's just where I started.
Regarding your first question on the chat, I couldn't type and listen at the same time, but there's a new paper or also videos, I think, on a new field. You asked about grammar algebra and NLP. Quantum NLP just is an emerging field, and Bob Koecki from Oxford and Cambridge Quantum Computing recently published in this area. So if you're interested, I would check that out.
I actually went to one of his one of the talks. That's how I got interested in it.
Cool.
So I think they also use heavily ZX calculus in their work, and categorical category theory and categorical quantum mechanics. And this MIT Topos Institute have a course on category theory. So that's where I'm planning to start my ZX calculus journey. So maybe you would want to check that out too if you're interested.
Yeah, definitely.
Yeah. And Alexei, about your previous question from end to end, are you talking about getting to know more about compilers and?
Well, I mean, first of all, because there is so much work done with simulators, right? I really want to see. I don't know if people have the same need, but right. I mean, like we've seen an example, like we did, had a kind of a study group with some friends, and so kind of, there's a QASM program, right? So you set up kind of a random walk for node random walk, and so you start basically by defining a circuit. So my immediate question is, is this a circuit like ENIAC? Other cables need to be connected, or is it, a state of, qubits, which basically, like you have. How do you actually program this? How do you get data in it, right? You initialize it. What does it mean? And similarly, right? So basically, I want to have a very kind of basic understanding of the quantum computer, and then how do you put data in it if it's not like random walk where you just randomly initialize stuff. Now you have actually to set states of things from classical data, then you can read it back, right? So first of all, I want to really understand how this is done, and then I actually want to, maybe it's just me, like a former physicist, but I really want to see that. Like is there any way for me to observe, right? Like let's have this quantum computer. I want to know. Here is, how is the classical bits are actually set, right? Here's how the computation happens. Then here's how they are read, because that, in my mind, this kind of learner I am. That would influence my further kind of understanding, because linear algebra is a very abstract way to model everything. So obviously, if you have an array of qubits, which are basically governed kind of by linear algebra, our understanding, right? I can then connect my understanding of linear algebra to this physical system. But the physical system in my mind, at least for me, comes first. And if you look how children learn, my 12-year-old, he disassembles everything. He wants to unscrew the screws. He wants to, like, he gets a toy with an LED. He wants to take out the screens, right, and see, like, he wants to see the buses. And then he takes a naked screen and connects it to something else. So it's probably how a lot of people learn. They need to see the physical. They need to develop an intuition for the machine, right? So for me, it's more important, because then I will figure out what do I need from linear algebra. I don't want to start with Lagrangian and Hamiltonian and so forth, because these are abstract concepts which people developed over centuries, you know, going from classical mechanics and physics. But you know, like I need to start with the physical system, and I need to actually see it works. Maybe, you know, it's all in our imagination. So I just wonder, like, if people are comfortable jump in with physics and quantum mechanics courses, or some people cannot do that before they actually see the thing work.
So for that, maybe I think you need some understanding of quantum mechanics to sort of appreciate what is happening, because and it also depends on the underlying system, right? So if it's superconducting or if it's photonic or ion trap, the entire I mean, so what you're doing is you're manipulating a quantum state, which is a vector, onto another quantum state, which is another vector.
Right.
So on the linear algebra aspect, it's the same, but physically how you do it sort of varies a lot. So for example, Xanadu in Canada, which is a photonic quantum computing group, so they are looking at measurement-based quantum computing, which is fundamentally different from PsiQuantum, which is another quantum computing photonic group, which also it's photonic, but they do a very different thing. And it's so physically, I mean, so I can't, at least for now, I mean, I can't directly see how you can first develop a physical intuition. But then again, that's because I'm a pure theory person and zero experimental experience. So, but yeah, and so for superconducting at Chalmers, we here, I mean, people who work on it here are working on superconducting devices, and they, and it's mostly, I think, like you said, like it's not cables anymore. You don't by hand set the cables, but it's electrical pulses. So you have a circuit that you make from superconducting materials. So you have something called Josephson junctions, which are made from superconducting materials. They're like a transistor, but different, because you have a whole set of different physics, and then you make circuits out of that, like normal circuits. And so those circuits are your qubits, and then you send electrical pulses to it to apply your gates, and you couple different qubits through capacitors, and it's, for me, it's a very messy thing that goes underneath. And so the gates you apply are the pulses that, or the electromagnetic pulses that you apply to those superconducting circuits, right? And so I know that Qiskit has like different layers of, I don't know the names. It's Qiskit Terra, Aqua, and something else. And it's like on the top of the stack where you just work with quantum information. You don't bother about the underlying hardware. And then you also have a way to control the signals that you apply at the hardware level to sort of maybe optimize your performance of the algorithm that you want to apply according to your application. So maybe that's of interest to you, right? You could check out the Qiskit layers. I think it's Aqua, but I'm not sure. Also CQC, right? Cambridge Quantum Computing that Mert was talking about. They have a compiler called TKET, which does this sort of same thing. It's like you give them a program, it compiles the program into the pulses that you want to apply to your quantum computer, and it takes care of that. And yeah, so to summarize, like 2 points, it's highly dependent on what kind of hardware people are using, and I think it's very messy, but
yeah, I definitely agree. So yeah, again, like I was gonna say the same thing. So Alexei, the problem with that is, first of all, you can't have a quantum computer at your house right now, right? I don't think you would ever have a quantum computer at your house. Also, this is recorded. If like 30 years later, everyone has a little quantum computer at their house, I don't want to be one of those people who are always
that did not age well.
You could have one, but I'm saying that it's highly unlikely. But again, the problem with that is like getting something and like unplugging it and like taking the screws apart, seeing what's inside. The thing is, there are so many versions of quantum computers, as Rishi said. So, and this reminds us of like the classical computing age, as you mentioned, like ENIAC and all of those. So before ENIAC, also there were many technologies, right? Not as much as we have right now for quantum, but there were a few attempts of building classical computers. We had the mechanical ones, and then vacuum tubes came along, and then transistor was formulated at, I think, Bell Labs, but I might be mistaken. There's actually a great book by Walter Isaacson called The Innovators that tells about the history of computing. So when I read through the book, I realized that we are in a very similar stage where computers are big and clunky and messy, as Rishi said. But we're also in some sense at a worse version of it, because there are so many technologies and there's so many attempts to build those, and on top of that we have the coherence. So quantum mechanics is by itself a fickle thing that every time you interact with it, it decoheres. So you can't keep something in the quantum level. So it's really hard to actually like interact with the thing. And I guess for people who want to see the whole process and who want to see what's going at the physical level, that's going to be a hindrance, at least at the start, until we have simpler simpler machines that, and then we after we see which technology works best.
And yeah, Alexei, just to add a final comment, you're not alone in this, that people would like to see what is going from end to end, right? Because right now it's very esoteric. And so IBM recently, maybe not recently, but had a roundtable talk where so Worley from Stranger Works was there, and this is exactly the same discussion that they were having. That people need to come and break things in different ways to sort of get the field moving ahead, right? Like you said, you have to sort of see what happens if I do this, but you're not intended to do that. No, what happens if I do that? And that sort of conversation going on. So maybe I can put a link to that also in the chat, and then it's basically the same conversation, but much better.
Awesome.
I mean, much more informed. Yeah,
that would be great to see. Yeah,
I can add one more thing.
Add that link. Please add that link.
Yeah, sure. Right now.
I can add one more thing about I feel like we're in an era where we don't know what the transistor is, and we don't know what the technology is that will be the underlying physical layer. I'm speaking more from a theory side, so I don't presume like a ton of knowledge here, but I do think that the circuit model for quantum computing is many people are developing at least algorithms based on the circuit model. Mm-hmm. And there are a couple simulators that you can play with the like quantum circuits using the gate-based model of computing, and you can see the resulting probabilities, and you can implement algorithms that people know, like QAOA or like Schor's algorithm, on these simulators, and that gets you kind of something close to the physical computation. But because that underlying layer is so system dependent, I think like this is like an interface that I know some theorists have aligned on. I'll send a couple simulator links in the chat.
Thank you. Yeah, I've put the roundtable in the chat. Right.
Thanks, guys. I mean, that was kind of my question, but maybe it's kind of my own kind of genetic predisposition, because I noticed my son is like that, right? And so, again, when we started learning computing, we kind of assumed transistors are given, right? Like classical computing was really way beyond that stage. So Kunal is right, and I mean, this is what I hear, that qubits are different. there is this and that, but that's fine. Like there is not infinite amount of those, right? So I guess we can still develop intuition, at least for instance, given that IBM Q network is the most broadly accessible one. That's kind of probably makes sense, right? And Qiskit seems well documented. So, you know, as Rishi, you talked, I just Googled like Qiskit pulse, and I immediately got into some kind of layer there, right? So like it's easy. At least I can follow that, and so that gives me an idea. So that's fine. That kind of gives me some pointers. This is just what I wanted to ask. If you guys feel other like pressing concerns, which kind of where you want to start, please ask this, because this is kind of for us all to address that, right? And obviously it's a safe place. Like people come from different backgrounds, like Nathan said. So it's really, there is no wrong questions. I mean, my kind of present question was end to end. I wonder what, and we heard linear algebra. I wonder what people feel like other things they need to get out of the way before they can learn.
Yeah.
Hey, I just wanted to talk a little bit. I think these are two really big, before we close this, these topics out, I've kind of taken Alexi's question and John Paul's question, because I think they're two huge areas for discussion. I just wanted to give a little bit of my input. So, so maybe starting with Alexi's question, I think the whole quantum computing industry right now, we're in this stage where we're searching for the killer app. So we're in the NISQ era, you know, Google did the supremacy thing, but there's a huge bridge to go from where that is to fault tolerant quantum computing, where you have very useful, you know, business applications in production and all that type of thing. So right now we're in a very primitive area. So without that thing that gets people really excited, like, oh, look what's going on in finance, look what's going on in pharmacy. There's a lot of cool ideas, but there's a disconnect because some of that's with pencil and paper. It's not really with code yet, just because the hardware isn't good enough. And you know, Mert mentioned Q2B. I think Q2B, QCware put out like a really good analogy right now, where they talked about the railroad and like promontory point. So right now we're in this stage where the algorithm and the theory people are getting better and better, and they're improving, and they're reducing the amount of resources that we need. They're working on one end, and then there's another end where it's the hardware people, and they're scaling up, they're doing more hardware. And, you know, we haven't come together and put the golden stake in promontory point yet to really, you know, say, okay, quantum computing's there. So this kind of NISQ area where it's very primitive, a lot of it is toy models. A lot of it is, you know, just going through the, you know, just the kind of boring mechanics of it. And it's, you don't necessarily get to that useful like business app at the end of the day. So I think some of the stuff that the annealing people do, you do see that where it's like, okay, this is a component that I can put together and put in production. So I don't know that much about annealing, but like it's something cool, like a startup like Chicago Quantum. It's like, okay, they're initializing, they're putting 40 different stocks in a portfolio, and then they run their optimization and they get something at the end. And it's cool to look at, but I'm sure Rishi and Mert probably know more about that than myself. But and then going back to learning stuff, I got a whole lot of overlap with the stuff that Rishi and Mert were mentioning. So I guess it's just because I'm a junkie for all the different content that's out there online. So I started with iTunes U, and it was like a good place to get all these resources with different theory classes and math and physics and everything. So I kind of am aware of a lot of resources that are out there. There's just so much diversity, even within something like quantum mechanics and quantum information. It's like, if you want to learn it from an engineering angle, there's like David Miller's course from Stanford. If you want to learn, you know, the physics stuff, and I'm looking at grad schools right now. So some of them are double E, some of them are computer science, some of them are straight physics theory. There's just a huge amount of diversity out there, even within the field. So yeah, if you're starting out like John Paul, I mean, yeah, the basic stuff is, yeah, like linear algebra stuff and vector calculus. That's like, you know, the foundations, a lot of that stuff, and diffie-q and all of that. But you'll probably pick that up stuff quick. And then, you know, it's just a matter of finding what you like and what, you know, course or whatever you like, and just sticking with it. So I don't know if I'm going to bust out my bookshelf, but I think everybody's kind of showed their books off already. But yeah, there's just so many different resources. I'll just say, to wrap it up, there's a course from a guy from Georgetown, and I met him once. It's like quantum mechanics for everyone, and he says he has like 100 different books just on quantum mechanics, and everybody has their own different take on it. So it's just interesting. So I just wanted to say that. Thanks.
Yeah, so where do you find these courses? I missed that.
Oh, the courses. So this was like a long time ago. iTunes U used to have a lot of the MIT OCW stuff that was on there.
Could you put a link,
and then once Coursera and edX popped up,
yeah.
I mean, if you just put quantum into edX, there's about 50 different courses that pop up. So like even before I did the MIT X Pro series, preceded that was the courses in quantum information science by Harrow and Schor and Zhiyong.
Yes.
So I think edX probably has more quantum courses than Coursera, but I'll mention too, this one, like if you're more into differential equations, Victor Galinsky from University of Maryland, Charles Clark have a Coursera course. I took it like 6 years ago, but they recently put that back online. I mentioned David Miller's course from Stanford. That's another different one that wasn't mentioned. But yeah, there's Coursera, edX, as far as like the theory stuff. Oh yeah, the other thing I want to mention as far as there's two different things. So getting back to what Alexi was saying, like say if you're a Silicon Valley person, I think I mentioned this a while ago, but there's an interesting concept from Matt Verstege, who's in Minneapolis. He's in a healthcare company, and he's building an internal team that has some quantum capabilities. So they kind of have two areas. So you have your concept area, and he was using the MIT X Pro series to just teach the concept, where it's like the quizzes are easy, it's more conceptual, the math is pretty basic, and then they just focus on programming. So just straight programming. I was going to post in the chat right now Eric Johnson's book. So Mert mentioned the CMU course, and that's more where they just focus on the programming. So that's an O'Reilly text that's in there, and it's like, okay. And I talked to the professor from CMU, and he said, yeah, they're just trying to yank as much of the theory out as they can and just focus on the programming, because that's what the kind of students go for. So if you just like need to get started quickly, that's one possible path. It's finding the path that's right for you, because there's a real diversity in the field. Like there's a lot of different ways to learn it.
Cool. Yeah. There's so much stuff, right?
Yeah, I have one thing to add. I don't know, everybody always talk about linear algebra, but they forget probability. It's like one of the important things on quantum is like getting understanding this notion of uncertainty, of having like multiple results on different, and how it's embedded in quantum mechanics. I guess is a really important thing that I guess as a physicist, I learned quantum mechanics due to all the calculus, and then after when I did a little bit of probability, I said, oh, are the same ideas, but apply it in this new system. And even, I don't know, Aronson in his book, he says, oh, forget about all the physics. Right. There's nothing. Quantum computing is just probability applied in complex numbers. So it's a really interesting thing to have in mind. Yeah, I also think, like Alex said, maybe there are things like just having this operational way of thinking in quantum mechanics is applying gates on everything. Is trying to forget about all these operations that happen behind, but you have like this new black box that you give the inputs and you have the outputs, and you have to learn through that. I found in one of the videos of Qiskit, they show these Qiskit blocks. I show the link. It's like how to practice your understanding on how the operation works. Is like a Minecraft clone, but using a lot of quantum operations. So you have to solve like puzzles, doing like quantum logic to find out. I found it really interesting of spending some time that I don't have. So
yeah, I definitely agree with the probability part. I think it's more necessary than linear algebra. I think Rishi's gonna object to that, but
I'd go for what I found interesting was the probability is straightforward. We're very, I don't know if I'm grateful or lucky for that. It's classical probability for the most part. Expectation value is average. And from what I see, most of it is based around expectation value. That's a classical concept. It's almost a high school concept. So I'm glad to get that one. That was almost like a freebie.
No, I mean, but
straightforward. The probability is pretty like surprisingly easy.
But no, I mean, if you go into more complex things, I agree with, I guess, having like good understanding of what a random variable is and so on definitely helps, right? So yeah. I mean, the sad thing is you need a lot of it. You need everything. So it's, yeah, it's difficult to say this more than that. It's again where you start from. So like Nathan was saying,
I think this is like a great field to get into, because you can like do whatever you see fit and whatever is more entertaining for you, and then you just in the end you're at the stage where you learn about many things.
Yeah, totally.
Not that I'm qualified to be anyone's career counselor at all, but from someone who's in the winter of their life, for you guys who are like in your spring and summer, there's a great future in this. Really, I think it's not only intellectually, I just think professionally, you know, you ended up doing well, no matter whether you're 20 or 50. That's
super
reassuring. I don't think it's going to go. It might not grow as fast as we'd like. I hope I see it in my lifetime, probably not, but it's definitely on the upswing.
Right. Yeah, this is something that I was super afraid of.
Momentum's building.
Yeah, it's like that was. I mean, so when I was taking a course in Leuven, one of the professors there, they did their PhD in spintronics, and after their PhD, all the funding in spintronics just stopped apparently, and they had to switch to some bio stuff. And I was like, oh no, is this going to happen to quantum for a while then? But now I'm more convinced, because I mean, even if it's, it's fine. I'm more set in my ways in quantum now. But thanks, Nathan. That's good to know.
Yeah, and one thing that I guess that we can leverage is like having all this information like almost for free, and having this is like a change of paradigm. It's like having everything accessible. Is like going to courses of any university on the planet that's posting that. It's like you won't have a time to see everything. So I guess like maybe you can choose knowing like or being like a specific and very specialist in one topic, or you can be a generalist and try to pick up from everywhere. But I guess like you will have to see what fits you more, because it's like people that I like looking at everything and knowing a bit of everything, and not saying I'm just the expert on how to tweak a circuit to do something, but I know people that doesn't work like that. So maybe you will, as you're starting like your career, you have to try out, and you have a lot of time and a lot of resources, or maybe opportunities that present in your life. I don't know.
Yeah, Augusto, maybe a side track. Do you know that ZX Calculus has like a Discord server that you can join, and they host weekly talks and stuff?
Oh no, I didn't know.
Check it out. I would highly recommend it. They're also a good community. So.
Awesome. I didn't hear you. Who's that again, please? Slowly.
Oh right. So it's another field called ZX Calculus. So like Jean-Paul was talking about. I don't know how related it is, but the same people are working on it. This quantum natural language processing by Cambridge Quantum Computing. I believe they use ZX Calculus.
Yeah, that's Kirka, Bob Kirka.
Yeah, exactly. So
diagrammatic programming, right?
Yeah. So they also have a book called Diagrammatic Programming, I think, with the dodo picture.
Exactly.
Yeah, and so I haven't read it, but they also say that it's a way to get started on looking at quantum from beginning. They don't assume anything that you need to do. And I have been working with tensor networks, which is another diagrammatic approach, and I love it. And it provides like a very straightforward perspective on what quantum advantages and when sort of algorithms can work and when they may not. So recently there was a paper by Miles Schrodemeyer and Weinethal. I don't know if I'm spelling the names correct. Hope they forgive me. But that said that lossy circuits are easy to simulate classically, right? And that sort of puts in question like Google's experiment. Is it easy to simulate classically? It's still on archive, so there's debate on it. But they use tensor networks and matrix product states to sort of come to that conclusion. And I can appreciate that because tensor networks is awesome. And yeah, so ZX Calculus, they have a Discord channel server. So maybe if you write to me later, I can send you an invite or whatever. And also Bob's book. It's super.
Thank you.
Yeah.
Thank you, Rishi. Yeah, by the way, we kind of said that this is going to be our holiday party. So I'm raising a glass of Duvel to all of you great folks, so maybe, I just wonder, right? So maybe we kind of can ask kind of a general life question. I wonder, what do folks want to do with this, right? So how many of you guys want to make a career in quantum computing, and what does it look like right now? I mean, I kind of I like Mert. I think is a great example because I see like Mert did this internship at QCWare, right? Right, but so you can get a degree or you can learn online course. I just wonder what folks want to do with it eventually, right? Like, do you want to work in this field? And if you do, like, what do you think the work will look like?
Honestly, I wasn't like, I didn't have in my mind that I would work in this field when I started reading about it.
Mm-hmm.
But it just like I can't seem to escape it. Like it's just I'm seduced and I just can't leave it. So I thought I would be like a product manager or like a quantitative trader, something like that does like math in a daily basis. But I didn't even think that when I first started, like there were career opportunities for people interested in quantum computing, because this was like 5 years ago, and it was still like an emerging field. One thing I wanted to mention this when John was here. So we work with John on the quantum workforce, and it seems to many people that you need a PhD to be a researcher or at least an expert in the industry. And we're starting to see this shift towards degrees that you can obtain in a smaller time. So especially for software jobs, so for programmers. So I went through a huge list of job listings in the quantum industry, and I saw that people are actually hiring more and more undergrads and master's graduates if they are looking for programmers. Of course, if they're looking for someone to like create a Josephson junction and work and maintain like a superconducting circuit, they ask for a PhD. But even this is like shifting, I think, and hopefully, like as the field matures, there will be more work-related opportunities. And yes, I would love to be in this field, in industry. I would be working on something that I do on my free time, and I would make money. That would be wonderful. So that's what I'm trying to do.
Exactly the same for me, right? So for me, during my electrical engineering, I was still interested in physics. I actually wanted to major in physics, but then, yeah, I didn't because for the reasons. And I was learning quantum mechanics I was not learning the courses that I was supposed to, but I was following physics courses on YouTube. And now I'm doing that, and I can call it productive work, right? So it's super happy for it. And I would like, so I'm more excited for the theory side, for the algorithms and what sort of applications that you can get out of this, and when you can get quantum advantage and when you can't, and so mostly the complexity theory side that Jamie was talking about and some others were talking about. So yeah, I'm super excited also.
Okay, is it hello?
Yeah, we can hear you.
Oh, sorry. I'm kind of interested in doing research in general. I'm interested in what will and won't be possible with quantum, and yes, quantum algorithms, but also all quantum technologies. So, like you said, complexity theory, and I've been reading about systems and systems thinking and impact and leverage points and stuff like that. So I really want to know, even without like a person with a quantum computer, how is this going to impact that person's life?
I don't think many people have answers to that, so it's a good place to it's a good place to work, right?
Like media loves to hype quantum computing, and this was like AI 5 years ago, machine learning 10 years ago, or it might be switched, but like and then VR, virtual reality, also like a few years ago. So I don't think people will notice something different in their lives for a bit, at least. But the stuff that we are, at least as researchers, we're able to do, and then industry people working on deep tech, that's gonna change drastically. So I don't think like someone who doesn't know about quantum computing and doesn't care about deep tech that much would notice anything different in their lives for the next 10 years. Again, these are not I don't want to be held accountable for these claims, but I think that for the next 5 years at least, we're going to see any dramatic change in the average Joe's life. But we'll see that we are able to solve many more problems that are impossible to solve with classical computers. Even if you had like the best computers, all of the materials in the universe like built into be a one computer, you would not be able to solve those problems unless you have a different way of computing. So those are definitely going to open doors. And what you can do, as Rishi said, we don't know. So the theory side, that's why it's interesting, right? There's always more theory coming out. We don't know if we can do actually more stuff or stuff exponentially faster with quantum computers for many of the problems that are proposed to run faster on quantum computers. So that's why it's exciting to work in this field.
Yeah, maybe if I can add to Mark's statements, it's that maybe even when you have fully functional quantum computers, the average person will not directly know that the difference in their lives is coming because of quantum computer, right?
Yeah.
So you may, I mean, people all over may change their encryption from RSA to some quantum lattice encryption, but mobile internet or like mobile banking will work the same. And people don't even the average person doesn't even know what RSA is right now, right? So they may not change, they may not understand sort of the underlying changes, but it'll definitely change. But it's an interesting question, right? So
it's kind of similar with AI. Not many people know how AI works, or they may be interested in it, but they don't know how like it impacts their lives. But if you're on Spotify, or Netflix, that algorithm knows you better than you know you, knows exactly what you want to consume.
Well, the thing about AI is it's relatable, right? Because we all have something, the I part of it, at least intelligence. So it's at least relatable. So people know about it. Like my grandmother at least knows about AI, but she doesn't really like know about quantum computers. So quantum computers are very they're not very relatable to our everyday experience. They're not something that we can think about or have a metaphor for. At least we don't have a metaphor for quantum mechanics. So it's really hard to like relate to that. So what media uses usually is the cryptography stuff. Like we're gonna break the RSA codes with Schor's algorithm and blah, blah, blah. Quantum hacking, China is gonna hack USA. Well, like the media loves to hype these things up. But again, as Rishi said, most fundamental changes in science and technology don't have an effect on people's lives. That's directly observable. That they make people's lives easier, and people don't really notice these because they are not. They're changes for the good, and people are better at adapting to these good changes. But if something like bad happened, then people would realize and that I don't think is gonna be the case in terms of like how the media portrays quantum in terms of like hacking and security issues, because we already have stuff that are not penetrable to quantum. We have quantum proof security protocols even before the hardware got there.
Although I agree with Mert that I think quantum computing is still in the fundamental areas of science, I do think that we do not know the full potentials of quantum computers. And so while we're saying that like it won't impact people's lives, we don't know what quantum computers can be used for. There were some recent papers in recommendation algorithms, people trying to augment machine learning with quantum computing. And then there were some proofs that the quantum algorithms were just as good as regular algorithms. So why do you need a quantum computer? But people are pushing at other, crazy problems, saying, can a quantum computer be useful here? And I think the most popular application that we know will work is in this RSA encryption factoring. So I think that's why there's more media exposure there. But if there are other really surprising discoveries on what quantum computers can do, then I think it may impact people's lives. It just depends on what they are.
Right, totally, right. And fun fact on what Kunal said, the person who showed that the recommendation algorithm, the proposed quantum algorithm is, I mean, there's a classical equivalent for that, was an 18-year-old, right? So their name was Evan Tang, and they were Scott Aronson's student. And so yeah, it's there, right? That's super cool. And also, I forgot the second point. Oh yeah, no, I had a question to Matt, but it's like, but it's based on D-Wave, and so I mean, feel free to not answer it. So it's I mean, could you comment on this? The amount of entanglement in D-Wave systems, is that because a while ago I think that was a huge debate, and then how quantum is D-Wave system really, right?
Sorry?
I mean, so the D-Wave qubits, do they have a lot of entanglement between them, or do you know about that?
I'm not sure. I think D-Wave is built on
superconducting.
Yeah, so the hardware is superconducting, but so it's superconducting flux qubits, but the way it works is it's not like our regular gate-based, circuit-based model where you entangle qubits. It's more like you have some quantum fluctuations and you kind of exploit the adiabatic computing model where you move a Hamiltonian using a transverse field and keep it at the ground state to a problem that you want to solve. And if it's at the ground state, when you're done with your cycle, you have a solution to your problem. But the thing about adiabatic computing is it's just really hard to do. So instead, you have annealing, where you have all the fluctuations while you're going through this process. And these fluctuations sometimes can lead to improvements. That's what my research was on, like in reverse annealing. But I'm not sure about entanglement.
Right. Okay. Yeah.
Yes, it is an annealer, Jean-Paul. That was your question in the chat.
Thanks.
So, guys, one way I'm kind of thinking about this, right? So I'm basically a community organizer in software engineering, right? And I partnered with IBM on AI and big data for the last 5 years, right? I mostly do my own independent community organizing in the Bay Area, but kind of we partnered with this, and folks who worked with me on AI moved into quantum. So this is how I got interested in this, right? And so what I'm thinking, kind of looking at the future, maybe I wonder if you guys saw that, right? But startups do this customer-driven, product market fit, right? Like they basically started the question. So there is this extreme school where you basically say you don't do anything until you talk to 1,000 customers. Like you talk to the customer, you want to do like a new dog product. So you talk to 1,000 dog owners, right? And you ask what do they want for their dog? Because if you have an idea, build it, and they come, you may be not doing the right thing. So I'm not sure if this is the right approach, but I think you always have to do that, right? The question, is it everything, or Steve Jobs basically said like nobody would think about the iPhone, right? Like he came up with an iPhone. Nobody would think of this except for Steve Jobs, right? He knew that you will need it. So what I wonder if you guys seen, maybe you've seen it like I mean, you can talk about customers, people who see that, but what do the customers think? Can we kind of crowdsource the meaning of quantum computing to a lot of people who worry about it? So, Kunal mentioned the RSA, right? And Rishi. I mean, I personally think that crypto is completely overblown. I looked at the blockchain field and like it now devolved into crypto speculation, right? Remember, we all talked about the world on the blockchain. Now it's all distributed finance. It shrunk dramatically into, a very specific area of crypto speculation and powered by cryptography. Like to my mind, it's actually insignificant because it's not obviously, it's not like creating drugs, it's not discovering oil. And if you look at some of the customers who look at quantum are Exxon, right? And they want to do exploration. It's pharma. They want to do protein folding, and it's finance, which basically wants to solve not crypto speculation, but they want to solve, I think, this quantum singularity, problem where suddenly somebody will come and take the whole like financial market by storm. So I see three things. At least I see the hearsay among the customers, right? So it looks to me it's kind of on the finance side is driven by fear that somebody will emerge, and one day our X will ring and they will come to the market. The opening bell will ring and they suddenly will defeat everybody, right? So I think this is probably what is driving this R&D investment in the top financial firms, at least how I see it from the outside, right? And then I see the questions like, obviously, finding oil, right? Obviously, British Petroleum, Exxon, they invested in big data before, and if they see that as a way to find more of this, that's kind of a very valid investment, right? You invest in exploration, and obviously, like protein folding, it's billions are spent, right? So I can also see the Department of Defense. I can clearly see they cannot do nuclear testing right now, rather constrained. So they were doing simulation already in supercomputers. I can very clearly see how they want to do it on quantum. So I kind of see these four maybe areas. I just wonder, do you guys think that we can kind of look at these customers, talk to them, and kind of see what they're doing as a driver of this industry, right? Is it kind of, because if we come from the startup approach, we need to see what the customers want to do, and then the solutions will be developed. I just wonder, what do you guys think about that?
I think so. There was a research on this. There was a survey. I can try to find it. I'm trying to remember the name. It's not D-Way, but it was a D-Way partner that did this. They surveyed the customers, and I think it's very comprehensive. So I'll share that. But from what I remember from it, people were interested in speed ups, at least. So not really like at least in finance, it wasn't like fear, but more of a competitive advantage that they wanted to have for themselves.
There's a key word you said there, speed up. I walked away for a second. I might have missed it, but what all those applications have in common, we do know what we want quantum to be doing, right? It's maybe I'm just being very naive. It's so simple. We want things to work faster. That's the basic attraction, right? That's the sex appeal, so to speak. It all comes down to that, and everybody wants that. So I think the question you're asking, Alexei, is well intentioned, but it's not well formed. It's almost impossible to answer. There's answers on both ends, and the industry will drive itself, right? And I just think it's fascinating that major companies, every major company, IT company, especially Google, Microsoft, Intel, Honeywell, and so on, there's some very smart people, and those are profit-driven companies. They can maybe put away 50, 100 million on a goofball idea, but they're putting in billions. So there's obviously a lot of smart people who think that something's going to happen. Unless it's the herd instinct, one person does it, then the second person does it, right? A great way to hold an event is to go to, get one sponsor like Google and then go to Microsoft and say, hey, you want to come to this event? Well, I don't know, but Google's going to be there. Oh, yeah? Well, I'm coming. And then you go to IBM and say, Microsoft and Google are going to be an event. And of course, they'll show up. So there might be some of that going on, but it's definitely on a momentum, which is cool. The rate of exchange, the rate of ascent, unpredictable. But as long as it's moving up, I'm cool.
Yeah, and to add to that, I mean, I agree with both Mert and Nathan, and maybe just to say, so one drawback that I could see just relying on customers or people for what they would expect or want a quantum computer to do is, like Kunal said, we don't know the full extent of what quantum computers can do, right? So, so this, going back to this roundtable discussion that they were having, so this is exactly what they were saying that. So Worley was saying that you need people, you need developers to come and break things in 1,000 different ways, and then for new applications to develop. So I mean, so it's important, of course, that there are people who can pay for this, and so that you have customers, but it should also be, I think, research driven, right? Because I mean, as a physicist, it's an interesting question to ask, like, what is happening? It's what's entanglement, and then like, why is this doing that, and why is it sort of being so spooky, right? So I would say that of course it is important that you have people to pay for it and you have customers, but the research aspect is also equally important. But this, I have zero experience in anything else other than academia, so yeah.
Yeah, this is interesting. To me, it's interesting that it's kind of it's a hybrid science / applied field, right? So I clearly see the kind of jobs which will always be available are to learn and teach, right? Basically, the best way to teach something is to learn something is to teach it, right? So academia definitely will always be a source of jobs. And so then I think the current jobs in industry are kind of R&D embedded in large companies. And so, some of this is it's the best of all worlds because they pay as industry, but they're structured as academia in a way, right? So I think this is kind of the dream jobs you can land right now, because apparently, from what I understand, the relationship between providers, right, like IBM and Google and others who want to cultivate the technology with the customers is essentially mentor-student, right? Like it's not scalable yet. You have to train PhD level employees in this, right? And so you only can partner reasonably with big companies like Morgan Chase, right, or Exxon, which have an ability to do that. And also, what I don't know, and it's very hard to understand how people like Goldman Sachs are doing this because they're extremely secretive, right? So and in some strange way, they're antithetical to academia because you do not talk about what you do in finance, right? So they swallow smart people, and smart people always have an urge to share and learn by collaboration, but these guys have to stifle it by dropping large bags of money on them from all sides so they cannot talk to each other, right? So it's kind of, I don't know really. That's why like we have some folks from finance, but they don't talk about it, right? And also people who do hardware, they don't want to talk about it, right? So because it's a secret. So I find it's very interesting that like we have some vestiges of academia, but the industry forces basically make it it's not fully scientific because there is a lot of money to be had by the winners, and that puts the whole pressure on this, right? And distorts, I would say, normal scientific exchange of opinion. So as an open source guy, for me, it's very interesting. How do you, like, maybe we can make inroads from open source, right? Maybe we can kind of see what we can share as open source, right? And kind of maybe the jobs will be, like, I don't know if the jobs will be more like Goldman Sachs or the jobs will be more like Google, right? Like, it's not yet clear to me where this whole thing is going. So I can clearly see there is a subset of jobs which will develop. I don't know what they will look like, and I don't know how many folks here want to work in a secretive field, like you don't talk about it, like somebody will actually, like, you'll have to get the permission to come here. I don't know if this is, where the field is going. I hope not, right?
Well, I actually, I don't want to interrupt you, Alexei, but I don't think it's as secretive as you say. So people in finance also publish papers. They just have some regulations that they can't talk about some stuff related to the company. Like Goldman publishes papers. I don't know about JP Morgan, but they also have a quantum team. And they're always in cooperation with universities and also other industrial players, also in their own game. So it's like they're competing, but they're also collaborating at the same time. And right now it's at a place where they're all intertwined because everyone is doing research. There's nothing else to do. Like, you can't actually do something that's useful with a quantum computer at the moment. So everyone is doing research, but it's gonna be more like you said, I think, as we move along, and people are gonna be more secretive, and people are gonna try to hoard IP into their company. But again, I think it happened with many emerging fields, right? It's always the case where it starts in a lab, people are doing research. We have people from academia working on theory, and then there's more money flowing in, and then people are like, oh, I can make more money out of this, and that even drives more research. Then we have more smart people putting their time and effort into this, and we have an industry in the end that's useful for everyone, for the whole world. So I think it's a process that has been proven to work in many other industries. But right now, I don't think it's as bad as you say. It's not as secretive, at least.
Right. I mean, I personally noticed it because I met some folks from hardware manufacturers, and they would just not talk about it, right? Because I think like, at least in terms of software, people will talk about it, but people who make hardware seems pretty secretive, because they don't want to say how far ahead they are, right? And so that was interesting to me. But again, I'm a software guy, not a hardware guy, so I know they're extremely different.
I think you pointed something cool out, Alexei, and this is just an outsider's perspective. But yeah, it just kind of reminds me of IBM and Google. So like, IBM has OpenPulse, so a lot of that's open source and you can access it, but they obfuscate some things because they don't want some hardware things being accessible or not. And yeah, now I've heard the same thing where it's like IBM and Google don't really, they're using very similar superconducting qubit technology, but they don't really talk to each other, and it's real kind of segregated. But yeah, I think some of that software stuff, and the same thing too, like Google, I guess, has their own software that they use. They don't use IBM stuff, even though they're similar things. So it's kind of a mix of both. I think software is just natural how it develops. In the classical sense, software is gonna have to pivot towards open source. It's just the better way to go. But yeah, right now the hardware, it does seem like they don't talk to each other about at least the people working on the bleeding edge, the people that are competing against each other. It seems like they're kind of siloed off.
Actually, that reminds me, strange. I mean, I like history of computing. You remember I think Shockley, who invented the transistor, had some very nasty personality, right? There was a lot of stuff involved in the early days, right? Because transistors, obviously, they're underpinning on this, and there was a lot of IP, right? And so kind of now, I think it's still happening, but we just do not, see it percolating. But obviously semiconductor industry, like, I mean, now there is a transition to Apple Silicon, even from Intel, right? Like there is a lot of tension who controls the processor, right? But it's just a different level. So I think that's an interesting way, right? Like Kunal said, like we don't know what the qubit is like, we don't know what the transistor is like. So whoever wins that race may dominate, the rest. So yeah, I don't know, like maybe in some way we have to wait, but in some other ways we cannot wait until we see who wins the transistor race. So we have to kind of put the cart ahead of the horse. So cool. So folks, I think we're a bit kind of running over what we planned originally. So I just wanted to kind of invite everybody to think, I think we have a lot of pointers. What about doing more kind of hands-on tutorials next year, kind of making it more of a study group, right? So I think we kind of, exploration versus exploitation stages. I think we covered a lot of exploration in the first 6 meetings. We kind of reviewed the field, right? And my mind was like, let's see where things are, who works in the field. So we start with introductions to kind of give people an idea where you're coming from, right? What you are working on. And I think we have a lot of learners here. So, right. So what do you guys think about kind of doing kind of more deep dives next year? Right. So like, I think MERS project, like end-to-end project, that sounds to me like a great introduction. Linear algebra obviously emerged as the next thing, right? Maybe somebody can cover physics. And I think from some of the meetings before, we had offers of this one-on-one tutorials, like we had physics from Oxford, right? Well, I think Alex Kissinger offered to kind of do with his group more kind of couple more like 2-3 hours hands-on keyboard dive. So I just wonder, what do you guys think about that? Like, would be folks be up for it? Is this something you can see yourself spending 2-3 hours doing? And can folks lead one of these things?
I would be super interested in that. Like learning ZX calculus is something that I already have on my checklist, and if like Alex Kissinger, one of the people, like main people who are working on it, can help me out of this. Like it's like a lottery, right? And so, I mean, I don't know. My experience is very limited. It's based on tensor networks and like the very small aspect of what I know. But I'd be happy to help anyone who's interested in tensor networks. So
okay,
yeah, I would be super interested.
Cool. Yeah, me too.
I'd agree. I mean, I got some exposure. I think there are a lot of great tutorials. The IEEE Quantum Conference kind of did a lot of that thing day by day, and I thought that stuff was really awesome. So I think if this group wants to do some of that, I think I got a lot out of that type of experience. So yeah, I'd be all for that.
Cool. So yeah, maybe what I'm gonna do next. And maybe we can work together on this, right? Let's just like kind of send a questionnaire to folks. What do they want to learn, right? Maybe kind of propose some of these topics and see who also can teach, right? Because we need a self-sustaining system where, some people will teach and some people will learn, right? So that, and obviously another question is, do we need quantum computers for this? Because I know that IBM Q Network can make some available. So I just wonder, like,
I think it would have a lot of more appeal if we had quantum computers. Like, we don't need them.
Mm-hmm.
Simulators can do everything, I guess, that at least the circuit models can do. Well, not everything. But stuff that for educational stuff, we could do everything with simulators, but it would have a lot of appeal if it feels different when you use a quantum computer. So it would be great to have like IBM partner with us and give us access to their devices.
Very cool. So yeah, I'll work on that then, as well, right? And see what they can make available and how, because I think, yeah, I mean, personally for me, it's a game changer because like, something happens there, like there is actual qubit, there is actual quantum state, right? You're affecting somehow. To me, it feels magical. Like I want to be able to do that, but then of course I need to see a proof of that, because what if my toy problem is connected to simulator instead of quantum computer? so we need to figure out how can we exercise actual quantum computer, and like be sure we did. So great. So folks, then let's do that. So let's kind of I'll share a survey, right? And so let's kind of see what we're gonna do next. And so obviously the next meeting will be the last Wednesday of January, which should be probably after everybody is back from the New Year's holidays, and hopefully a lot of people will get vaccinated, right? And so the world will hopefully reopen at some point. We'll make I normally run physical conferences of about 1,000 top kind of computer scientists in the Bay Area. So I really hope I will be able to do that in the Bay Area. And so hopefully I will partner with Quantum, Stanford Quantum and Berkeley and others. And the idea was always we'll take it around the world. So when the world reopens, hopefully we'll partner with IBM, bring it like to London and EU in some way too, right? So, but before that, like let's plan some online learning, and so I'm super open. Like I don't know, exactly kind of what will happen the next year, but I really appreciate the folks kind of could help me. I mean, Merit and Stanford Quantum did a lot of great work already, stepping up. If folks want to help me organize this, I would really appreciate it. So Rishi, you're very welcome. I think you've been instrumental in this, right? I'm glad to see like new folks like Nathan with really cool resources. So if any of you guys feel like you want to lead on these tutorials, if you want to pick like an area, right, carve out a direction where you want to do, like for instance linear algebra, feel free to take it and kind of propose to not just do one tutorial but a series, because at this point I think we need to kind of set up a study group, and we need to kind of individual events, but we also need kind of an idea whether this is going. So let's plan some time, spend some time planning that, and kind of start new year and like really get more into learning.
I will, Nathan here. I'll reach out to you when you do the survey. You'll include your contact info.
Yes.
And I'll reply.
Absolutely, I'll do that.
Right. So it looks like we're wrapping up, but can we set up like a deadline on when to send the lists that Mert and I have? So if I understand right, Mert, are we collaborating on making this
Absolutely.
list? Or?
I mean, if you can share by the end of the, I guess like, like 1 week from the end of the year. So I would say like, depending on your holiday plans, I would say a week or two is fine, right? Like,
Right. So in 2 weeks.
1st of January, 2021.
Yeah.
First.
Okay. Yeah, let's do that.
Let's do that. And so everything which we discussed, I will save the chart obviously as well, and kind of extract some of the URLs. But Mert and Rishi, please converge on a Google Doc, send it to me. I'll publish it. Yeah. All right, and we'll and also I'll mention what Nathan has sent already, and so hopefully we'll take it from there. And and then if you have any idea of leading a tutorial, let's discuss it in more detail.
Yeah.
Cool. And I want to thank everybody. That was a great year in terms of learning. So hopefully it will be even better next year. Thanks for making this series a success, and thanks for participation. We'll learn something. So cheers to you, and see you in the new year.
Yeah.
Thank you. Yeah, I hope to see you everyone soon. I think this is a really small field. I think I saw many of your faces before. I'll see you guys again. Thanks for coming, everyone.
Thank you for having me, and thank you for being here. And also happy holidays.
Happy holidays.
And stay safe.
Yes.
Bye. See you.
Cheers.